Hi everyone, and welcome to this recording for relativity. It's going to be about the special theory of relativity, and let me put it in a context basically to see what happened when we were around the turn of the century in the going from the 19th century to the 20th century. At that time, Mr. Maxwell came up with his four equations basically. Actually, it's a little more than that, but at least he summarized the work of the people before him basically and his contribution to it too, namely that the divergence of the electric field is equal to the distribution of charges basically in the medium. And why is the pencil writing at some sort of a slanted format? Okay. And that of the magnetic field is always zero, indicating that the magnetic field is always curling basically, going around, doesn't diverge. And then also that the circulation of the magnetic field is of course proportional to the current that causes it. That's really what creates. So that's the current density. Plus another contribution that Mr. Maxwell added to this stuff, and that has to do with the so-called displacement current, or the rate at which the electric field is changing with time. And then of course the last equation is Ampere's law, that basically, no, this is Ampere's law, is actually Faraday's law, that state basically that the circulation of the electric field, normally the electric field according to the first equation doesn't circulate, except now when the magnetic field changes, or the flux of the magnetic field changes with time, then that yields a new kind of electric field which actually circulate, and it's given by Faraday, and the minus sign is due to Mr. Lenz. Well, these equations are not compatible with something that is really important, that was actually from even before Newton's work, and that is due to Mr. Galileo, that he showed basically, he argued that the physics should not matter, or at least if I go from a frame to another frame that is moving with constant speed, I should not really find a different assessment. In other words, here is the scenario. Okay, and we saw this in physics 1. If you're riding a train and jogging in the same time at 6 miles per hour in the train, and it's fast, by the way, 6 miles per hour, and the train is moving at 50 miles per hour, and if you're here in the station, this is you, the observer, and trying to basically see how fast the person in the train is moving, you clearly see that it's 50 plus 6 is going to be 56 miles per hour. The reason why that is because of the following scenario. And I know we did this argument a long time ago in physics 1. So basically is the following. So here is this situation. This is the external observer, so I'm going to call him O, and I'm going to use the references where X is for the position. I'm going to take the one-dimensional case, and T is for the Y-axis. This is the so-called Minkowski representation, basically, of space-time. And this is the moving train. This is the train that is moving with a velocity v, basically, with respect to the observer. Sometimes we use it u, the letter u, but it doesn't matter. So this is the coordinates x prime, and the as they are labeled in the train. So that's how we got the 6 miles per hour. And of course the time in that frame, which is t prime. Obviously, in the old mechanics, in Newton mechanics, the time was universal. So if we sync our clocks now, they're going to stay synced forever. So there was no notion that time may be different from one observer to the other. So as long as v is constant, this v is constant, then in this case we have what is known as inertial frames. Okay, these two frames are inertial frames. In other words, they move with frames with respect to one another with constant velocity. There is no experiment that you can do in one frame to distinguish that you are actually moving and the other one is not moving, because as far as the person sitting in the train, he is stationary. The observer O prime is stationary, and he sees the entire basically universe is rushing in the opposite direction with the speed of the train. So that is actually the perspective that we have to look at it. So in this coordinate system, if I have the object in here is labeled by the position x prime, of course I'm using just 1D, so this is the position x prime, and if the train is moving with the velocity v, so that means this distance is v times t. So it's clearly, for my labeling outside, of the same object with position x, that x from this simple geometry is x prime plus vt. I mean, I should really put t prime, but t is equal to t prime, so it doesn't matter which t I should put in there. So that's basically how I can label it from this vantage point. For the observer sitting in the train in here and marking this locations, that person sees the position x prime as referred to by the position of the stationary observer. The observer at rest is actually x minus that same v times t. And in here I probably will use the letter t, but as I said before, t and t prime are the same. So because there was no notion then that time may be different between two different inertial frames. So that's basically the notion that we have in there. If you are curious into what that means in classical mechanics, this is Galilean relativity that you guys have done in physics 1. Basically take whichever expression you like and take its derivative with respect to time. So if I take this with respect to time, that gives me the velocity as measured by the observer O. That is the person sitting in the station. This will be equal to the derivative of x prime with respect to t prime, and that with respect to t prime, or with respect to t, I'm sorry, in here, the derivative with respect of t or t prime is the same thing because it's the same value. So this will be my 6 miles per hour, the example I gave earlier, plus the derivative of vt prime with respect to t or t prime is going to be v, and that in my example was the 50 miles per hour, and hence the observer sitting in the station, he sees both of them coming toward him with he sees the train coming with 50 miles per hour, but the jogger actually is running faster ahead of the train by 6 miles in addition, so 56 miles per hour. So that's the notion that we have in there. If we take this expression and take its derivative one more time, we'll find the acceleration, if there was, if all of a sudden, for example, things starts to accelerate, if the person decides to accelerate. Remember, v is constant. We're assuming this inertial frames, and that by definition the train has the cruise control on at 50 miles per hour. So if the jogger, for example, decides to accelerate or decelerate, so in this case I'm going to take the acceleration for the jogger A is equal to the second derivative of x with respect to time, and that, according to this expression, is the same thing as the second derivative of x prime with respect to the same thing. T doesn't matter in here, it's the same time, plus the derivative of the speed of train, which has to be 0 in this case because I'm assuming inertial frames. In other words, if I know the forces that cause this acceleration, I can say that F equal to ma, and this is a prime, by the way, and in the same time it's equal to ma prime. So in other words, the physics doesn't care if you do an experiment, for example, on this jogger, or trying to find the forces on the jogger, or equilibrium, or whatever you want to do. It doesn't matter which frame you do. You can't tell actually that the train is moving at all. You do it in the inertial frame that is in motion, or you do it in inertial frame at rest, you will find the same physics. You will find the same results in the experiment. In other words, excuse me, if I'm sitting on the train, for example, and take this object and throw it in the sky, it's going to go up and down. Let's say, for example, I want to know the time of flight. So it leaves my hand, goes up in the air, stops and comes back. Time that, use the mechanics of Newton, and then I will find the time. Well, it went up and down, I can find the time. For the observer sitting outside in the station, if you throw the object up and down, it's actually going to follow a projectile. It's not going to go straight up and down, it's going to follow a projectile. And if it's the same thing, I'm trying to determine the time of flight, it's going to turn out to be the same answer. And actually that's a problem that is typical in physics 1 that you guys have solved. So the time is the same regardless of the observer. As long as these observers are not accelerating, as long as these observers they have a speed that is constant between them. So that's something that we knew from the time of Galileo, even before Mr. Newton and Einstein and everybody else. The problem with these equations is they're not consistent with that. Actually, there is a problem in the homework that you guys can work on, or we're going to do it actually in lecture, that we're going to show that there is a problem with these equations. For example, it yields to the wave equation, and the wave equation that we know, for example, is for this one, after we solve it and fix the polarization and take care of the direction of propagation of light and all of that, is the second derivative, for example, for the electric field and that of the magnetic field is going to be the same thing with respect to the displacement direction. So this electric field must be either in the y or z direction, minus, because I took the direction of propagation of the wave in the x direction, minus 1 over the c squared, where c squared has to do with the permittivity and permeability, mu naught and epsilon naught in these expressions. It's actually exactly 1 of square root of c is 1 over the square root of that product of those two constants, times the derivative with respect to time. The second derivative with respect is equal to 0. This turned out to be the wave equation. This wave equation is exactly incompatible. If you try to change coordinates in here from x and t to x prime and t prime, even with t equal to t prime, you will find that this equation is not does not stay the same. There will be additional parameters in it due to cross derivatives. So there is a problem in here. This equation is invariant, is actually not invariant, it changes under Galilean transformations, which are these transformations. These are the Galilean transformation from one frame to the other and vice versa. Okay? And this equation, if you like. Okay, so those are the equations. So there was a problem. We know there was a problem. Furthermore, Mr. Michelson and Morley tried to determine the speed of the Earth with respect to the medium where this wave would propagate, namely they called it the ether, and he found none. And more experiments on having a source of light, for example, moving and trying to determine its speed, the speed of light that is, using the fact that this expression will hold true for light too. What is it? This one, that the velocity of light now with respect to an observer who is sitting outside, and if I'm on a train, for example, shining light at him, it should be the speed of light plus the speed of light plus the speed of the train or the speed of the source of light. And we will never be able to do that. So there was a problem basically abound at that time, and Mr. Einstein had to basically came up with a new theory, and that is the purpose of this topic, to explain this thing. So came up with two postulates, which constitutes the question of the first question of the day, and that is to put these two postulates in your own words. Okay, here are how he put them. First of all, the laws of physics are the same for all inertial frames. In other words, if Mr. Maxwell were able to find that this wave propagates in a rest frame at this with this phenomenon, and was able to find the speed of light, and he was able to find everything in here, and he was able to find the frequency of the light and everything else that you like, and whatever experiment you do in this frame and the other frame, the physics in here is invariant under basically going from one inertial frame to the other frame. I mean, that means immediately that there is a problem with these transformations. They are not correct. We have to fix them because they are not working in here. Okay, so that's one thing. The second postulate he made, because of the fact that the experiments that were conducted on light, and actually because of some ideas also that he had about how information travels actually, is that the speed of light is the same for all inertial observers. Okay, as a consequence of that, it will turn out to be that the speed of light actually is a Mach speed. Nobody can travel with the speed of light. Nothing can travel with the speed of light. Okay, at least it has mass, and you will see that. Okay, so those are the two postulates of relativity. So let's see how we can fix these transformations so that everything works. Okay, so the first thing that we will need is the following. We're going to make the following. We're going to go back to the inertial frames that we discussed earlier. So we have the observer O with Minkowski space, in this case x and t. I'm not taking y and z. I'm assuming that they are perpendicular to the x components in here. So we're taking motion in one direction only. Okay, so to make things simple, and we have x prime for the observer's second oops, man, this thing is tilted. Okay, so that's a problem. Let's move it down. Hopefully I can have a better control over this. Sorry guys. Okay, I'm gonna leave it there. And t prime, okay? So that's the observer O. I'm assuming in here that t and t prime may not be necessarily the same. I'm not saying they're not, but they may not be the same quantity, okay? So we're allowing for the possibility that the clocks are not the same. The reason why we say that is the following. If I'm an observer in reference frame O, and I send a beam of light, for example, from my point in here, my starting point, and to a certain distance that I know specifically how far it is, where, for example, light will hit something and trigger something, and then I can see the time, basically, I can measure the time it took for that distance, I can find the speed of light in this frame to be simply equal to the ratio of that distance traveled by the beam of light divided by t. So this experiment can tell you clearly how x and t are related in my frame. If I do the same experiment in here, the second postulate states that for this observer now measuring a distance x prime, which may not be the same because of the fact that this is moving with a velocity v that is constant, okay, in the x direction I'm assuming to be. So in this case, then x and x prime cannot be the same, therefore also t cannot be the same if I expect to have this ratio to be the same. Let's say, for example, x is twice, or x is twice x prime. So if I have a 2 in here, I must have a 2 in here to cancel so that I end up with the same ratio. So the possibility of time not being the same is actually necessary in here to meet postulate number 2. But how different? That is not stated in postulate 2. We have to find it, basically. Okay. So postulate 2 now, because of the fact that the speed of light is measured by two different observers measuring two different values for the position, they have to have different denominator if we expect this ratio to be the same. So in other words, in here, x prime is equal to ct prime. Okay, so that's basically c is the same. The speed of light is the same for both observers. So this is a specific event where we fire two different basically we fire the same light beam and locate its position with respect to my frame and your frame, and I'm using a clock and a ruler, and you're using your own clock and a ruler. So in this case there is a problem, because let's say, for example, x prime is less than x, so I can tell you, hey, listen, there is a problem with the way that your measured distance is, your ruler is short. Or you say, no, actually the ruler that you're using is too long. Or you say, okay, maybe your clock is then, since the ruler is short, then your clock is ticking slower. For some reason there is a matter with your watch. You say, no, actually the problem, my watch is perfectly working fine. It's the watch that you have that is moving too fast, or vice versa. Okay. So in other words, this is basically a problem now of basically an issue because of this transformation. The fact that these two frames are moving with constant speed with respect to one another. So here is how to solve the problem. The relationship between x and x prime need to be, because at some point we need to agree on the physics. Go back to physics postulate 1. So we need to do the same thing, and we'll find the same acceleration as everything should work. So let's see here how we can fix, among other things, Maxwell's equations need to work in here. Okay, so let's see here how we can fix this issue. So what I'm going to say in here is the way that I measure distances. Remember, x prime was x minus vt. Now it's going to be x minus vt. So if you give me your x minus vt, which is the way you measure x and t, I'm going to say, okay, rescale that value because of the fact that the rulers are not necessarily the same. So if you wish, that parameter gamma that I wrote in here, please do not confuse this gamma with the CP over CV from way back in chapter 20 when we dealt with the adiabatic process, okay? It has nothing to do with molar specific heat at constant pressure or constant volume. So this is just a factor to account for the fact that the scaling in here of the ruler and the clock may be different, okay? So that is actually the tinkering parameter, the parameter that allows us to move from one frame to the other. So we need to find what that gamma is, actually, to make things make sense. So we're saying in here, your ruler and my ruler, because VT is actually a distance, are factored in with this factor gamma, okay? that is because I see you moving with the velocity v in the positive direction. So you know what? I see you moving in the negative direction. We're moving with the velocity. So if I give you x prime, I need to add to it vt prime to find your x. And gamma here must be the same. Because as far as I'm concerned, you're moving back with a negative v. You're moving in the opposite direction with a negative v. So as far as I'm telling you, your x, the value of x, is actually nothing but the x prime that I measured in the moving frame, and plus the vt prime that I measured in the frame. The reason why I have to have a plus because you're moving in the negative direction. That's all. And the factor gamma need to be the same. So the factor gamma either cannot depend on velocity because we just switch signs for the velocity, or gamma can be an even function of velocity. So that's the requirement for gamma. In general, gamma has to be an even function of v, because we are requiring it that if we switch from frame to frame, the sign of v switches and gamma stays the same. So if that's this thing, then what we're saying in here is that gamma of v is the same thing as gamma of negative v, if it depends on v at all. If it doesn't depend on v, that's fine. Then it's the same thing, okay? So that's the function gamma that we need to find as a function of velocity, because that's the requirement that we're saying in here. So let's find gamma, okay? And then we will solve our problem. So these two equations, of course, if I multiply them side by side, I end up with a new equation, and this is true all the time. X prime is equal to gamma squared times these two products. X times x prime is x prime. Okay. X times vt prime is v times x times t prime. And then I have to do minus vt times x prime. Minus vt times x prime. And then finally, minus times plus, that's minus again, v squared times t prime. Okay? So that's true no matter what's going on, because these two transformations are expected to be compatible. So we're going to go back to the same experiment that we did earlier. We wait until we pass one another. Okay? So the coordinates are the same. And then we sync our clocks. And we fire a beam. Okay, I know where the beam is going to hit. It's going to hit at the position x. Okay, you know where the beam in your frame is going to hit. It's going to hit in x prime. Okay, you measure the time because you're moving with the velocity v, and you find it to be t prime. I measure the time in my rest frame, and I find it to be t. So in this case, that's a special event that has to do with light. Okay, because light is the same for both frames. So in this case, if I take these two expressions and multiply them by one another, this times that, this two basically, I will find x times x prime. So let's write them. X is equal to ct and x prime is equal to ct prime. Let's sub everywhere in here. X times x prime is going to be c times t times t prime. So it's going to be c squared times t prime, okay, equals to gamma squared times the same quantity in here. So that's c squared times t prime plus v times x. X is ct, so it's going to be plus vc t prime minus vt times x prime. X prime is ct prime, so it's going to be minus v times c times t prime minus, that doesn't change, t prime, v squared t prime. Well, these two quantities are clearly the same thing. They cancel. Okay. Furthermore, there is cancellation on both sides. T and t prime, and t prime. And now we have an expression for gamma that doesn't depend on this event and must be true all the time. C squared is equal to gamma squared times, I am left with c squared in here, and I'm left with v squared in here. So everything cancels in here. And if I solve this one in here, move c squared to the move this expression to the denominator and take the square root. So it's going to be basically this. Okay, let's write it down. C squared over c squared minus v squared. Okay. and then divide c squared in the numerator and denominator, I'm left with 1 minus v squared over c squared. That means that gamma itself is just the square root of that stuff. Remember, this is a scaling factor. This is basically how to change rulers. The rulers are positive, so I'm going to take the positive value in here. It doesn't make sense to take a negative value in here. Okay, so I found gamma, and indeed this is an even function of v. If I change v to negative v, v squared stays the same, so gamma meets this requirement, so this must be true all the time. Okay, the factor gamma, I'm going to define a quantity in here. I'm going to define beta to be simply the relative velocity of their frames with respect to the speed of light. So that means that in terms of beta, gamma is equal to 1 over 1 minus beta squared. It's just a convenient way of writing this expression, that's all. In particular, if I want to rearrange this expression here a little bit, I can write 1 over gamma squared is equal to, after I square this one and flip it, it's going to be 1 minus beta squared. This relationship will become useful very shortly, okay? Remember, beta is nothing but the ratio of the two velocities of the inertial frames with respect to the speed of light, that's all, okay? And from this expression, we can clearly see that beta cannot be equal to 1. Beta, no matter what, v cannot be equal to c no matter what. It's always less than, because I will have a square root of a 0 in the denominator for gamma. That means this blows away. That means it doesn't make sense. Or cannot be actually greater than 1, because if beta is greater than 1, if v is greater than c, we have a problem. We have square root of a negative number, which doesn't make sense. It's an imaginary number which don't make sense in real physics. So you cannot do an experiment on that to find a ruler that is imaginary. Okay, you lost your ruler all of a sudden. So so that's really what I said before, that this will become the fact that no matter can travel faster than the speed of light, of course except light, because that's fuzzy. This equation, which is with which it travels, that's c is the speed of light. Okay, so here is where we stand right now. So we found that x equals to, let's write x prime first. X prime is equal to gamma times x minus vt, and we found also that x equals to gamma times x prime plus vt prime. Okay, it would be nice now to find the values of x and t in terms of x prime and t prime. That means if you give me your position and time measurements, I can give you my position and time measurements, and vice versa. So we really need to find the transformation. For right now, they don't look clear, because we have x prime as a function of x and t, and we have x as a function of x prime and t prime. So what I want to see is an x prime and t prime as a function of x and t, period, end of the story. So for that, we have to solve these two algebraic equations. So we already have x prime. All we need is to find t prime from the second equation. So basically, let's divide by gamma everywhere in here and work out this algebra. So what it says in here is that x prime plus vt prime is equal to x over gamma. And I know what x prime is. It's this expression. So that means vt prime is equal to x over gamma minus this stuff, minus gamma times x minus vt. I have a minus times minus, it's going to be a positive, and I have a gamma in front of it, so I'm going to leave that. So I'm going to leave gamma everywhere out. So it's going to be gamma out of everything in here. So like I said, I have a minus and a minus, that's a positive vt. Okay, that started with t in here because it's easier. And then I have an x over gamma where I took another gamma out. So I'm going to have, with a positive sign, that is 1 over gamma squared, and then I took that gamma out, so there is a minus 1 in here, times x. Let's divide by this v, and we're done. We found the transformation. So this is t prime equals to gamma times, okay, 1 over gamma squared minus 1. I just said that 1 over gamma squared is equal to 1 minus beta. So 1 over gamma squared minus 1 is going to be negative beta squared. So this thing is actually negative beta squared. or if you wish, it's negative v squared over c squared. Okay, it's from this expression above. That's all. 1 over gamma squared minus 1 is equal to negative beta squared. So let's write this stuff in here. So we're dividing by v now. So the v cancels the v. So we're left with t, I'm sorry. And then the minus sign. And I have a v squared now, and I divide by v, so I'm left with a v in here. And I have an x in the numerator, vx divided by c squared. So let's summarize these expressions now, then, what we have. We have, first of all, x prime is equal to gamma times x minus vt. We have, I'm going to write y. We didn't change that. We didn't really move in the y direction, so it must stay the same. And z is z prime. And t, I should have written the t and the t prime in the opposite direction because I'm moving from one frame to the other. So let's be consistent, that's all. Let's delete that. And let's delete that. In other words, going from one frame to the other, we want to be consistent, that's all. So this will become, not that type. This will become prime, and this will become prime. And then we have t prime, per that last equation is gamma times t minus x, or let's write the v first, minus v x over c squared. And that is basically the expression that we have found going from the coordinates x, t, y, and z to x prime, y prime, z prime, and t prime. If you like to write the other equations and solve for one of them, is already given. We know that x is equal to gamma times x prime plus vt prime. That we have started with, actually. And then we have now y is equal to y prime and z is equal to z prime. And if you like, you can do the calculation for the time, and you will find the following expression. Gamma times t minus becomes a plus, and then you have v x prime, here t prime, divided by c squared. Okay, these are the expressions that you will. The reason why I don't need to really do the calculation, I know this is the correct answer, is just by symmetry. Okay, we just went from one frame to the other, and we made the argument that this, I see you moving with the velocity v, you see me moving with the velocity negative v, so all you're doing is taking these expressions and subbing the primes where they were primed, and removing the primes from where they were primed, and changing the sign of the velocity from positive v to negative v. So that's the same thing. Okay, but if you like, you can derive this expression by solving for t in here and subbing the value of x from this expression, and you will find this is true. Okay, where gamma, as I said in here, is a tinkering factor in here. This is the factor that you play with to make this thing happen. Gamma is equal to 1 over square root of 1 minus beta squared, or 1 minus v squared over c squared. Okay, this has a name now. This whole transformations have a name. They're called Lorentz transformations, and this is the Lorentz factor. Okay, so that's basically how these things work. Part of the problem that we're going to do is to check that this equation is invariant under these transformations. This equation stays the same under these transformations, and all of mechanics stays the same. Obviously, F equals to ma becomes a problem now because it's not going to work under these transformations. This equation in here becomes a problem. What is it? When I was doing this transformation, so it's going to be a problem because I have a denominator now. I have to take its derivative with respect to time. So in other words, classical mechanics now fails. So we have to find a solution for it. So this is the Lorentz transformations, and they're crucial for almost every math. And here sometimes they are taken as a postulate too. Okay, so sometimes you can say just simply because they're equivalent to postulates of relativity. Let's talk about something. One of the consequences that we did way back when we were doing waves, and that has to do with the Doppler effect. The Doppler effect is the following. Okay, I know for slow speeds, it's not going to matter much, but for high speeds, it's going to be a problem, okay? Especially if we're doing astronomy and things like that. So we really need to correct that phenomenon. Let's talk about this. We have a light source, okay, that is in its own rest frame. It's before I do that, let me talk about a couple of things in here that we can go back into these expressions in here and take two specific phenomena. One of them is a phenomenon at the same location. Okay, I think it's already 35 minutes and we have quite a few ideas to add more. So we have still the topics to talk about is the time dilation, the contraction of length. We're going to talk about the Doppler effect, and we're also going to talk about the mass energy equivalence. So I'm going to leave that for a second video because this video is already 35 minutes, okay? So I'm going to stop.